Okay, you can see here.
Okay.
It's okay. It's recorded. Yeah.
Hello, everyone. I'm Nezam Rohbani from BSc. I finished my PhD in Sharif University of Technology. And for a while, I was working as postdoc in Institute for Research in Fundamental Sciences, IPM, in Iran. And now I am a research engineer in Barcelona Supercomputing Center. Okay, the topic of our presentation is about DRAM memories. At the beginning, we will have a short talk about the DRAM structure. Okay, it's working. And a short introduction to DRAM, about its structure and limitations, and the past, and a little bit about future. And we will have a short discussion about one of our previous works, which is related to DRAM reliability. And after that, we will have another discussion about in-memory processing. We will have a look to the previous works. And later, we will discuss about one of our works about in-memory processing. Okay, as you know, DRAM stores data in tiny capacitors, which normally in recent technology is something, something around 20 femtofarad, which is super tiny. And as you can see here, simply by activating a word line and activating the access transistor, we can access the memory cell to read or write in that. In many cases, it's called DRAM is volatile, but we cannot tell that simply, because in very low temperatures, it turns to non-volatile memories. It can store data until few minutes in the power out situations. But still, DRAM is the best candidate as main memory, almost in more than 40 years. But here, as you can see in this chart, in different generations of recent DRAMs, although the bandwidth grows very sharply over time, from DDR to DDR5, and in DDR6, which will be available very soon, it would be more than 100 gigabytes per second. But as you can see, the cycle time, it's remained almost unchanged over time, over like more than 20 years. The cycle time is something like 15 nanoseconds, and it didn't change over time. The other issue with DRAM is that it's power hungry. For example, as you can see in these rough charts, for mobile devices like mobile phones, tablets, or small laptops, the power consumption is something between 20% of overall power consumption, which is dissipated in DRAMs. But it can rise more than 50% for servers, especially in memory-bounded workloads. And as you can see here, almost 30% of total power consumption in DRAM memories is devoted to leakage and refresh operation. And 70% is to activation and cell access. But these values can change a lot based on the workload that is working. And here in this figure, you can see its effect on the performance of the different workloads that are executing on the system. And again, in memory-bounded applications, the effect on performance is huge. Therefore, DRAM is lazy and power-hungry at the same time. Here you can see, we can have a simple look to different families of DRAM structures that are DDR for normal PCs or laptops, and GPU bounded, which are GPU centrics, which are GDDRs or HBMs. Recently, we will have a short discussion about HBMs, which it's almost 10 years that they are announced. And after that, low power DDRs, which are used, as I told, in like mobile phones, tablets, and small laptops, and embedded DRAMs, which we will discuss them shortly too. As you can see, the operating voltage is more or less for many of them. only in low power DDR, the input output voltage is reduced to be able to reduce power consumption. But in all of these structures, the memory access style and the hierarchy of memory is more or less the same. Okay, let's take a short look at to the DDR structure, which is used in almost all of the PCs and high performance computing. As you know, DRAMs can be seen generally in dual inline memory modules or DIMMs, which recently can reach up to 256 gigabyte, the largest size as I know. And the input output is still for a long time 64 bits address and data input output. And the power consumption in the idle phase is something like close to 2 or 3 watts. And during full active memory access, the power consumption can reach to 12 watts or even more. But as you can see, each DIMM is made of 8 or 16 chips, which you can see the schematic of the DRAM chip here. Here we have I/O pads at the center for the input-output data. And generally, a chip is made of 8 to 16 banks. Each bank is a unit that can fully separately work in parallel with the other banks without any intervention between them. And the last technology for DRAM fabrication is 1 beta, which is something close to 10 nanometers. As you know, the technology size like 2 nanometers is getting famous, or 1.8 nanometer is getting famous recently for fabricating CMOS devices. But in DRAM technology, this value, the highest technology is something close to 10 nanometers. The reason that we cannot reach to the smaller sizes is because of the DRAM memory capacitor. We cannot make it very small because we can simply lose our data because of leakage. But what's inside a memory bank? Memory bank contains some peripherals like global row decoders, which partially decode the input address, and column decoder, which fetch the data from the cells and pass it to input output. And more important, it contains sub arrays, which are made of multiple memory arrays, which are called MATs. MATs are two-dimensional memory arrays, which are made of memory cells. As you can see here, the memory cells are one in between are connected to left and right bit lines. All of them are not connected to one bit line in a row. And I will tell you about the reason. And by activating one cell, which will connect to one of the bit lines, the sense amplifier will compare the voltage on one bit line comparing with the other to detect the input data which is stored in the memory cell. As we told, the voltage is very tiny on this cell, and by connecting this cell to the bit line, a very tiny voltage perturbation will occur on the a tiny voltage perturbation, not as easy as reading, like it's a bit more tricky. Amplifier, which is made of 3 different parts. One part is used to pre-charge the bit lines to half VDD, which is 0.1 volt, almost 0.1 volt in the recent technologies, which will pre-charge all of the bit line pairs in our DRAM, this simple 3-transistor circuit. And we have the sense amplifier, which is made of 2 cross-coupled NOT gates. And here we have the access column select lines. But how memory access works? It's quite simple. By activating a cell and connecting it to one of the bit lines, as we told, we have precharged the bit lines to half VDD already and floated them. A small voltage perturbation, which is something close, will be generated on that bit line which is connected to the cell. And after charge sharing phase, by activating this sense amplifier using these two transistors, M4 and M9 in this figure, this cross-coupled NOT gates will start to amplify the input. If the voltage perturbation is slightly higher than 0, this voltage will be amplified to VDD, and the voltage on this node will drop to 0, and vice versa. If the input signal is less than 0, the voltage on this node will drop to 0, and this voltage will be rise to VDD. And in this way, we can detect the input, the voltage on our cell. But when we are sharing the charge between cell and the bit line, of course, our charge in the cell will be diminished, will be eliminated. Therefore, in this operation, the sense amplifier will write back again the read data into the cell. And the recovery phase is happening during accessing the cell. Okay, these needs different cycles, which are the most important timings in DRAM memory access is TRCD, which is the time needed for activating a row and reading in that row in the sense amplifier and be able to access the data in the output. And column access time, which is TCL, which is the time we need to activate the column select line and read out the data from the sense amplifier. And pre-charge time that we told, we need to pre-charge the bit lines before accessing a cell. And read and write and refresh operations in DRAM is almost the same, very close together. Almost all of them need an activation and the cell access. Okay, here you can see some limitations about DRAMs, which I will not talk about them so much. One of the biggest one is requiring for refresh operation, which can be 64 milliseconds to 32 milliseconds in recent DRAMs, and it's decreasing over time because we need to refresh the cells faster and faster. And another issue is row hammer, and that I will talk about it, and it's getting worse and worse in the coming generations. And the other issues that I don't want to focus on them so much because I want to preserve time for the other discussions. But the most important benefit of DRAM is its maturity and it's cheap. And making it is not, fabricating it is not very expensive, and the technology is mature enough, and therefore it's almost all of the main memories in all of the computing systems. Our DRAM is the dominant technology, and in my mind, it will remain for a long time. Here in this table, you can take a look, take a look at comparison between DRAM and other technologies like PCM, RRAM, NAND flash, and SRAM. And as you can see in all of the aspects, DRAM has something good to remain as main memory in the computing systems. Okay. Another, I will have a short talk about high bandwidth memories, which are recently getting more and more important in the high performance computing, especially in GPUs and the bandwidth bound workload operations. As we know, in DIMM structure, dual inline memory modules, we have a very long distance between the processing element, which can be CPU, and the memory modules. And this long distance that can reach to a few centimeters, we will lose a lot of energy and performance, and we will have a lot of delay for the access to the cells. For this problem, HBM is introduced that the memory modules are stacked together, like DRAMs can, like up to 16 different layers of DRAM dies can stack on top of each other, and they can connect to each other through TSVs, through vias interconnect. And they will be connected to the high bandwidth bits memory controller. And through an interposer, they will connect to the GPU or another processor. Here, the distance is in the order of few millimeters or can reach to 1 centimeter. Therefore, this short distance and a lot of memory data, which, for example, in DDR is 64, and here we can have up to 2,000 data links between our memory system and our GPU. Therefore, the bandwidth for HBM is super huge comparing with DDR and even GDDR, which is used for graphic cards. Everything is almost all of the aspects of HBM is better than the DDR and GDDR, but there are some problems. The most important one is HBM is super expensive. Stacking different layers of DRAM to get on top of each other can reduce the yield in the fabrication because if even there is a fault or error in one layer, all of the batch should be throwable. And another big issue, which is a good topic for research, is thermal management in HBMs, because we can have up to 16 different layers in our HBM. Power dissipation and cooling of the structure is super expensive and not easy. Therefore, in fact, increasing the number of layers more than 16 is not an easy task. But because of the very great bandwidth that these memories deliver, they are getting more and more attraction from the different companies to fabricate. And the PIM, or processing in memory, which we will talk about it later, is getting more famous in these type of structures because we can have one extra layer for our processing elements, and the data access is very, very close, less than 1 millimeter here in this case. Okay, another DRAM family is embedded DRAM or eDRAM, which the operation, as I told, is more or less close to the normal DRAM cells. But here you can see 3 transistor, 1 capacitor structure of embedded DRAMs. The most important benefit of embedded DRAMs is that they can be made in the same chip that we are making our CMOS. And those are CMOS friendly in another term. But DRAM memories are not CMOS friendly. They're needed to fabricate it in another chip, and they can be stacked on top of a CMOS chip or something. But embedded DRAM can be made inside the CMOS chip. But as you can see, the number of transistors is 3 times of one normal DRAM cell. And another issue is that accessing the cell is different from the DDR or normal DRAM. Simply by activating the right word line, this transistor will be activated, and we can simply write in this cell, which it can be a capacitor, or it can simply be the gate capacitor of this transistor. Maybe this cell, this capacitor even cannot exist. And during read operation, we can simply activate the read word line. And if we have 1 here, this transistor will be activated. Or if we have 0 here, this transistor will be turned off. And the pass-through read bit line to the ground will be full or will be cut. Normally, these type of families, embedded DRAMs, are used for on-chip memories like large L3 or L4 caches. They are slower than SRAM, but faster than normal DRAMs, and they can be fabricated inside the CMOS chips. Okay. We had a short discussion about DRAM memories. Here you can see the timings that we talked about. Of course, timing is much more complex than what we discussed. But in short, there is something interesting in DRAM memories comparing with some other technologies, is that when we even want to access one single bit of data in our DRAM, normally, for example, in DDR, 64 kilobits will be activated. The 64 kilobit is the smallest chunk of data that we can access in DDR structure, DDR5, for example. This is because we can reduce the peripherals to access the data during using this large number of activations. And we hope when we are activating 64 kilobits, we can, if we are lucky, the other accesses to the DRAM cell will be hit through those cells that we read already. Therefore, when we open a row, we will not close it. We normally keep it open, and we hope other accesses from cache controller, which is the memory controller of our processor, will be hit in that row. If we are lucky, it's like a row hit in a cache memory. But if we are not lucky, we need to close that row. That means we need to pre-charge all of the bit lines, all of that 64 kilobit lines again, and open another row, which imposes a lot of energy and energy consumption and delay to our access. But one of the reliability concerns that I want to have a short discussion about that is row hammer, which is detected in 2013 or 14. And that's because of the leakage issue in DRAM memories. As we told, we have different leakage sources in our DRAM, which can be through our access transistor or inside the cell or between the gate transistor and word line. And this leakage will eliminate the data that we have in our cell, and we need to refresh it again after like 32 milliseconds. But in row hammer, what is happening? With a very simple code, if we activate one row multiple times after each other, like by activating and deactivating one of the rows, the adjacent rows, which are called victim rows, may lose their data. And this can simply happen in the recent DRAMs. And you can simply download the code from the internet and run in your laptop, and you will see this happens in your DRAM structure. The number of activation and deactivation for the attacker row is something, it's very different in the different operating conditions and the vendor of the DRAM and the other aspects, but it can be something to like 10 kilo activations and deactivations, and after that, you can expect the adjacent rows start to lose their data. A lot of previous works have proposed to detect a row hammer attack and resist against it. And many of them are based on counting the number of activations on a row. But there are a lot of problems with this technique because it has a high overhead when we are just because we need a counter for each row in our DRAM, and we will update the counter after each activation of a row. But not only the overhead is the problem with these techniques, but another problem is that since row hammer effect is very sensitive to temperature and process variation, these techniques are not aware of temperature and process variation. They just count the number of activations on a row, and if it reaches to, for example, 10K, they detect a row hammer attack. And there are some other limitations with these techniques because recently some of the attacks became more mature, and they break the attack to multiple small chunk of activations to hide themselves from the counter to detect them. Therefore, to detect all of the row hammer attacks in our work, we propose the technique that is made of just one single extra DRAM cell in a row. For example, in this figure, we have one dummy or extra non-operational cell in each row, and this cell will be accessed exactly the way that the other cells are accessed and activated and deactivated at the same time. And these cells are connected to a detector circuit that you can see here. The structure is quite simple. As you can see, we have a dummy cell or extra cell here. And when one of the rows, for example, this row, start to attack the other row, this cell start to lose its charge, the same as the other cells in this row are losing their charge. And when this loss of charge, which means increase or decrease the voltage on this capacitor, reach to the threshold voltage of this transistor, this match line will be connected to the ground. It will be grounded. And it can simply be detected and raise a alarm signal in the output. We can have two different circuits for 0 to 1 or 1 to 0 bit flip, which its overhead is quite small for these two circuits. And using this circuit, all of the different temperature condition, part of process variation, and all of the attacks that can change the adjacent capacitor's charge can be detected through this sensor. And comparing with the previous techniques, its overhead, especially area overhead, is very smaller. And by this simple circuit, we can even detect which row is attacked by just connecting these discharging transistors in a binary manner to the different sensors that we have here. We can detect from the output which row is attacked, and we can simply refresh that row, or we can send an alarm to operating system to detect the application which is attacking, which and it can control it or do something and increase refresh rate or something else. Okay, here you can see some HSpice results. You can see the sensor output that after detecting the attack, it started to rise or fall for different 0 to 1 or 1 to 0 attacks in these figures. And it's interesting that, as we told, the refresh rate for in DRAM cells, especially for DDR5, is 32 milliseconds. And when the attack is happening is important. At the beginning of the refresh time, the cell is more robust against the attacks, but it starts to lose its robustness against different attacks. And here you can see the effect of temperature on the number of required attacks to make a bit flip. And here you can see how accurate the sensor is in the presence of process variation. Okay, I do not talk about them so much. I try to reach to the in-memory processing part. Okay, as you know, there is a big issue for a long time, which is called memory wall. And this is the problem that we shortly talked about. Accessing to the data out of CPU or GPU cache levels is super expensive in terms of power consumption and latency. And this gap is growing over time. And therefore, since the data movement is costly and it's a bottleneck, a lot of techniques are proposed to perform in-memory processing, like processing our data near or inside our memory. There are different approaches for this, which two main categories are near memory processing and processing using memory, which is normally called in-memory processing. Near memory processing is based on putting some logic circuits inside the memory structure, like close to the DRAM structure or inside the DRAM cell. And processing using memory, or PUM, or processing in memory, which we are focused more in this work, are trying to use the memory cells themselves to perform this operation, generally in analog or digital manner. But the most important issue with in-memory processing is that the fault rates start to increase because many of these operations are performed in analog manner or semi-analog between analog and digital manner. The rate of faults in these techniques increases. Here, I brought some of the most important previous works, like one of them is Ambit, which is very fundamental in the in-memory processing. The operation is very simple. Instead of activating one row at a time and accessing to one cell, this is our sense amplifier, as we told, two NOT gate that are connected as cross-coupled together. Instead of activating one row, 3 rows will be activated at the same time. And as you can simply understand, a majority operation will be performed between these 3 cells. If 2 or 3 of these cells contain 1, the output voltage will be 1. Otherwise, the output will be 0, which is the majority operation, and you can almost perform all of the other operations using majority operation, like AND or XOR and others. But the issue with this is that the perturbation signal generated using this technique in the worst case is worse than normal DRAM. Therefore, a simple noise in the environment can destroy the accessed data. Another in-memory processing we can say is simply row clone, which it's quite simple but very effective. If we want to copy one data from this row to another row, which can be here the destination, we can simply read the data in the sense amplifiers, but we will not close this row. At the same time, we will activate another row, and it automatically will write back all of the data to the next row. Therefore, in 2 cycles, we can copy a huge amount of data from one row to another, which is super important for many operations. Another technique is ROC, which is famous too. The structure is quite simple. It uses one diode to do the in-memory processing. For example, in this sample in figure B, first, we want to, for example, perform OR operation on X and Y inputs. First, X value will be copied to cell C, and in the second phase, Y value will be copied to cell D. This is done. The output result will be stored in the cell C, because if both are 0, of course, the cell C will contain 0. And if one of these 2 cells or both of them contain 1, the cell C will contain 1 too. With this structure, we can perform more complex operations like AND or XOR and other operations. But as you can see, again, we are using a diode, which is made of one transistor in this figure, which we will have a threshold voltage drop on this diode. Therefore, the stored output is not exactly VDD in this cell, and this can lead to data loss. And here another one is ELP2IM. It's a bit more complex. I will not focus on it so much. And here, as you can see, we have a sense amplifier and pre-charge circuit. But the sense amplifier is not working using VDD and ground voltage. It's working with VDD, ground, and half VDD voltage. Again, here, since it's like VDD, it can be very sensitive to the environmental noises. Okay, but the technique that we propose is on performing XOR operation, which is very important for many applications, especially for binary neural networks recently. We can perform XOR operation inside DRAM structure only in 3 cycles using our technique, which is far better than the previous techniques that are proposed. Here you can see a simple schematic of the proposed technique. We added an extra cell, which is called X cell, This cell is a bit more complex than normal cells, but it has this benefit that it can connect to bitline left or bitline right, as we have extra transistors here. The operation goes in this way that, for example, we want to perform XOR operation on A and B cells. In XOR operation, it's working in this basis that if B is 0, we will have A, or if B is 1, we will have A naught. And okay, we have a message here, I think. No. Okay. If B is 0, we will read A. If B is 1, we will read A naught. Therefore, in this simple circuit, first we will read A and copy it to the X cell, which we have a cell here, using that row column technique, which needs one cycle. In the next phase, we will read cell B in our sense amplifier. And in the next phase, which is our third phase, based on the value B, which can be 0 or 1, one of these transistors will be activated. We will activate both of these transistors at first. And if, for example, we have B0, the value B naught will be 1, and this will activate this transistor. Therefore, A will be read through this bit line. But if B is 1, A will be read through the opposite bit line. Therefore, the NOT operation will be performed in this cycle. Very simple, and the output result will be XOR operation, which will be stored in the sense amplifier. And we can have the chain of XORs on as much as data we want, but we should be aware that all of the XOR operations should be performed on one bit line pair, not the adjacent bit line pair doesn't have access to each other. And this is actually a big issue with in-memory processing that we can talk about that later. The other operations like AND, OR, NOR, and other operations are taking less or equal time of XOR. But the main focus in this work has been on the accelerating XOR, which, as you can see here, the proposed technique is much faster comparing with the other previous works, because all of the previous works till now are using simpler operations like AND, OR, and NAND or NOR operations to perform XOR operation. But here we directly perform XOR and XNOR operation in our DRAM memory. Okay, this is about latency and the power consumption of the... Okay, I try to finish it faster. On the inside the DRAM memory using memory cell. This is, as I mentioned, this is PIM, processing in memory, or PUM, processing using memories. And since all of our operations are fully digital, like rail to rail, 0 to 1 operation, our technique is very much more robust against the environmental noises and process variation comparing with the previous techniques. Because all of the previous techniques use something like semi-analog operations, they are very sensitive to the noises. Okay, I finish here. As we discussed, DRAM has been the most important memory for main memories, and it will, as I think, it will remain the most important technology for main memories for a very long time. HBMs will be probably more attractive in the near future because of the AI applications and GPUs, and especially bandwidth bounded applications. And at the same time, in memory processing, which, for example, the companies like Samsung focusing on, they propose like in memory processing techniques using HBMs or near memory processings in HBMs and other DRAM circuits. In the near future, HBMs will be very important too, because they can perform parallel operations fast and at the same time reliable. Okay, thank you very much for your attention. I'm here. If you have any question, you can turn on your mic or you can write in the chat box. Thank you so much.